Good morning, everyone, and thank you for joining us today in the third session of our Nature Inspired Solutions webinar series. Today, our topic is clean energy and resource efficiency, and we've got another incredible lineup of speakers with us here this morning. My name is Emma McKenna. I'm a knowledge transfer manager at KTN, and I lead our Nature Inspired Solutions Special Interest Group. And I'm really kind of pleased to be here and chairing the session again today. Before we kind of get into the swing of things, I just want to run through a little bit of housekeeping. This session will be recorded. All attendees will be put on mute, but if you have any technical issues, so if you can't hear or see me, please pop any messages around kind of technical problems into the chat box, and my colleague Poonam will be on hand to kind of hopefully help out with that. Also, as well as that, if you've got any questions for any of the speakers throughout the session today, please do put them into our Q&A box, and myself and my colleague George will be keeping an eye on those, and we'll be putting those forward to the panelists during the Q&A session of this webinar later on. And if I haven't said already, yes, it is going to be recorded today as well. Just to kind of let you run through a bit of the agenda, if you have joined these sessions before, we're taking a slightly different format today because we've got 4 or 5 speakers joining us. We're going to do a really short intro, 5-minute intro from each of the speakers, and then we're going to get into a much more lengthy Q&A panel discussion this morning. Just because with our last session, we found that there was loads of engagement from the audience. There was lots of questions being asked, so we just wanted to make sure that there was more opportunity for that discussion and to kind of get into the details around nature inspired and clean energy and resource efficiency. So it's just a little bit of a welcome from me. I'll set the context, we'll do the panel introductions, and then we'll have the Q&A, and we'll do a short summary and close. We know that as well that these webinar sessions, we can get into some of the details of the conversation, but we want to really continue that conversation to keep it going. So as before, like other webinar sessions, if you'd like to continue the chat and continue speaking to other participants and kind of get into the details of this, then please do continue the conversation on our application called Meet and Mojo. It'll be open from 1 to 5, and you can sign up and book 1-to-1 10-minute meetings with other attendees that are here on the webinar session today. And this is just the link just kind of on the screen that you can click onto, but we'll also share the link to this on the chat box as well if you'd like to get involved in that too. So what is nature inspired? I know that our audience that usually joins these webinars can kind of come from mixed backgrounds. Sometimes we get those that are kind of, you know, nature inspired advocates and really kind of are working within this industry and really know it well, and you're looking to kind of see and explore how it might be applied within clean energy and resource efficiency. Likewise, we might have people that kind of come from an energy background or resource efficiency and are really keen to understand what is this all about around kind of nature inspiring kind of new ways of working within those sectors. So when we talk about nature inspired, what we mean is rather than imitating the whole plant, animal or biological process, nature inspired solutions aim to uncover underlying mechanisms and apply them in the design of new products, processes or systems in a structured way. And so what we want to do is kind of explore how nature inspired can be used as a methodology and how we can apply that to a whole host of challenges or sector application areas. And today what we're doing is we want to explore what role nature can play in our transition to clean energy and resource efficiency. As the UK, we've made quite an ambitious and inspirational commitment and legal requirement to hit net zero by 2050. And there's going to be no kind of one solution fits all approach to be able to help us achieve that. And so within this discussion today, we want to see if we can take inspiration from nature to help us achieve those clean energy and resource efficiency goals. Because if we think about nature and how it works, it always finds the most efficient ways to be able to do things, and it does so in harmony with its surrounding environment, something that we as humans aren't always so great at. So by taking inspiration from nature and applying it to these challenges, hopefully we might be able to learn something. And so that's kind of the basis and the context for the conversation today. And each of our panelists are experts and specialists and researchers researchers in various different areas, and they will be kind of exploring the different aspects of this within a kind of a much larger umbrella of clean energy and resource efficiency. So I'm just going to stop sharing my screen now, and also stop talking, and hand you over to our very, very first speaker of this morning, which is Marc Olivier, who is the Director of Centre for Nature Inspired Engineering at UCL, and also heads up chemical engineering there as well. He also sits on our advisory group at the Nature Inspired Solutions Special Interest Group, and was one of, I suppose, one of the inspirations as well for us setting up the Special Interest Group to have this focus on nature inspired solutions within the KTN. So I will pass over to Marc Olivier for his short introduction.
Thank you very much, Emma, for this nice introduction. A pleasure to be here on this panel discussion. And indeed, I'll introduce very briefly what the Center for Nature Inspired Engineering is doing, and I think we can learn some lessons from nature for energy and resource efficiency. So the way we work at the CNIE is that we're really driven by a number of the challenges, and they're framed by sustainable development goals, including the one related to energy and to water, that is very pertinent to the discussion today. And at UCL, we also have a grand challenge on transformative technology. So 2016, which is looking at how we can derive new innovation and technology that can benefit the society, but also the planet. And so we hear the word transformative here, because if we want to address serious, great, grand challenges, we really need not to be incremental, but be transformative in our innovation and do this in a responsible way. We're also driven by the industrial strategy. And one of the key topics pertinent again for today is the one of the clean growth in the UK industrial strategy. So I'm a chemical engineer by training, and I like to show this picture where we see a picture of a so-called modern chemical plant on the right and one from the 16th century on the left. And we see a lot of similarities in these vessels and series with stirs. And so one can ask the question, what is really fundamentally new? And perhaps we should be drawing lessons from nature to truly innovate and come up with more better designs for sustainability. And so when we look outside, we have other reactors there. We have this walnut tree, which is in my garden. And you see this tree is also a chemical reactor, and each of the scales is important. The nanoscale is important for photosynthesis and for capturing that water and CO2 and turning it through sunlight into the biomass that makes this tree grow and produce oxygen. But then also the mesoscale, the structure of the leaf, is pertinent, and the structure of the tree crown, which is scaling. It is a self-similar scaling structure. While the tree grows, it just has more and more branches, and the scale of the smallest twigs remains the same at all scales of this tree. And that is something fascinating, and it's very different from the way we scale in industry typically. So nature-inspired engineering for us is to learn from the architecture and the dynamics of natural systems at all scales to help design and synthesize innovative, superior solutions to technological challenges. And these relate, for example, to energy, resource efficiency, and topics related to sustainability. Where we go is that we really need to think about the fundamentals. And that is key. It's not biomimetics in a narrow sense. It's not just pure imitation. It's fundamental mechanistic understanding, right, of how this tree, for example, works, and not imitating things out of context. So not directly copy nature into a solution, like you said in your intro, Emma. So what we need for this is then also a methodology. And that's what we've been focusing in the CNIE on what we call nature-inspired solutions for engineering, and is in a systematic way, look how we can find design solutions to challenges going from nature to a particular application. And this is based, as I said, on mechanisms. And so we look at a variety of mechanisms. Clearly don't have time to discuss them all at this moment, but we look first at these hierarchical transport networks, like you see in the tree and the structure of the lung. But we also look at other things like force balancing, which occurs in mechanics, of course, like in bones and in trees at large scale, but also at the nanoscale. And we look at dynamics, self-organization, even the structure of how sand is organizing on a beach, thanks to the gusts of wind. And then most recently, we are looking at ecosystems, networks, and modularity. What can we think, what can we learn from the networks approach about how organisms work together or how you have networks from genetic networks, metabolic networks, all the way upwards. That's really key to resilience in nature. So behind each of these mechanisms, you have concepts that nature employs for scalability, for efficiency, for resilience, and that's why we can learn from this. And by having this thematic approach, learning from each of these mechanisms, we can then systematically learn from nature to drive an application, and we can also influence lateral thinking. So we can solve a problem in one area and then use that solution in another area as well. So one example is learning from the structure of trees and lungs. And so by which we have developed a fractal structure to distribute fluids very uniformly over a vessel, just inspired by the tree. And when you scale that up, instead of making everything the same but larger, we just change the number of generations, just like in that tree. And in this way, we have very uniform distribution over a vessel and can mix more uniformly and can scale the system much more easily. We've applied this to a concept important in renewable energy, which is in fuel cells, right? And fuel cells are devices to convert chemical energy into electrical energy. But the PM fuel cells using hydrogen as a fuel also have challenges because the catalyst is expensive. There are mass transfer limitations, there are stability issues, and issues of the water management, the water that is formed and is not removed very easily. And so we take this inspiration from the structure of this trunk, of the lung and of the tree in scalability to design new flow plates to very uniformly distribute the air over the flow plates, over the catalyst of these fuel cells on one side and the fuel, the hydrogen on the other side. And so we take then a systematic approach, learning from the structure of the lung, not imitating this, but using this as an inspiration for the optimal distribution through these fractal plates, flow plates that we then realize through additive manufacturing methods, like 3D printing methods, which can now be done to make this very uniformly distribution over a catalyst, which is also hierarchically structured. And in this way, we can achieve much higher current densities and power outputs with a fuel cell. So we take this approach at multiple scales. So again, the macro scale, the mesoscale, the nanoscale, all of them are pertinent. So all of these scales can teach us lessons in nature on structuring catalysts, on the distribution networks, through transport towards the catalytic sites where reactions occur, and the macro scale of the whole device, right? Now, the water that is formed in these fuel cells also needs to be removed. And there again, we take another principles from nature. We look at the so-called thorny devils, which are creatures living in the desert that take their water from muddy puddles, and through passive transport, it goes to their mouth. And so they can extract small amounts of water in this way. And this is through capillary action, right, that you have this. And these principles are used in the fuel cells, but we also use them now. We have a student in the group, Malika Schmidt, who's an architect by training, showing how we really work across disciplines to develop coatings that we are envisioning for control of humidity, which you could use in the built environment, right, on panels, but also use for space technology, which is where we want to test this first. So we're working now with the German airspace and the European Space Agency, where we have parabolic flights planned, where we have nature-inspired coatings using this capillary action mechanism to control the water flow and take humidity out and recycle the water. Because when you want to go to space missions or even in the ISS, it's extremely expensive to bring water there. So in these extreme environments, these are very good test grounds to test principles of how you could preserve water. And so with these specialized nature-inspired coatings, with these pillar structures inspired by these natural systems, we could recycle the water more, we could preserve water more. And so this is what we're going to test soon. So Malika is actually on her way to test with parabolic flights now with ESA, this type of coatings, and we hope to test these out in the International Space Station as well. And then this might be helping us also for resource efficiency here on Earth. Right, so this is a close-up of what we made through 3D nanoprinting, these little structures, which are very beautiful as well. So they even came in an exhibition in the Centre Pompidou last year, and where water is channeled through this bottle-shaped structure very effectively and can be removed in this way. So on the level of dynamics, we are in engineering very often looking too much into constant flows, right? Like in reactors with constant flows. But when we look at dunes, for example, or we look at beaches, we see these regular patterns through the action of the gusts of wind. And so many things in nature are breathing, we breathe in and out, our neurons are firing. These are dynamic structures. And through dynamics, you can get much more structured systems as well, more efficient structures. And so we use this, for example, for drying. So instead of having a constant flow on a powder, you can use a pulsed flow. And in this, we have much more uniform drying overall. This is also important from the energy point of view because operations like drying and coating and so consume a lot of energy. And so thinking just differently out of the box is also something very fascinating one can do out of nature. But in the end, we need to think about how this works, the mechanisms behind it, and that is key in our approach. So it is not just being obsessed by nature by itself, but always thinking about the context. It's not because nature has evolved to be where it is that it necessarily satisfied a particular purpose in solving a problem, say in energy or in energy efficiency or resource efficiency. Always we need to think about the context. But there's clearly such a big book of nature which we can learn from. And so I look forward to the rest of this discussion. And so I could only give a very short overview. So looking forward to our panel discussion. Thank you.
Thank you so much, Marc-Olivier. That was great. It was really great. I think it was a really great set kind of introduction and kind of setting the scene much better than I did at the start, and kind of really giving a little bit of a flavor of some of the things that you're doing at kind of the Centre of Nature-Inspired Engineering, and kind of where this might take us, and kind of all of the opportunities. So really looking forward to kind of, I suppose, looking into that a little bit further, and kind of, I suppose, looking at kind of what the potential of that might be a little bit later as well in the panel discussion. So thank you so much. Up next, I'm going to really quickly introduce our next speaker, which is Raffaele, who comes from the School of Engineering and Physical Sciences and is the Chair of Chemical Engineering at Heriot-Watt since 1989, and was also named one of the top 100 most influential women in the engineering sector in 2019. So really, really honored and pleased to have you here today.
And I would like really very much to thank the organizers and Marc-Olivier today for having me here. And I think that Marc-Olivier has said many things that probably I'm going to tell you in this very short presentation, which shouldn't last more than 5 minutes. So I would like to speak to you about modeling, because this is essentially what I work every day about. Now, modeling is a term which is very much used nowadays and include physical modeling as well as computer simulations with commercial software, for instance. However, I believe that underneath every model, there is a mathematical representation of a physical or natural phenomenon. And speaking specifically on my work, I can show you something with a figure. Now, if you look at what we have tried to do in many years now, scientists have tried to break down, analyze the matter, and going from what we observe macroscopically down to the constituents. And Marc-Olivier has very well explained what is about macro, meso, and micro levels, and I don't need to go through that again. What we are trying to do with model, we are trying to do the other way around. In other words, what we are trying to do, we are trying to start from the detailed molecular model, and through model simplify what we observe, and through simulations, we are trying to reproduce what we can observe at the very large scale. In other words, what we are trying to do, we are trying to have the right sum. We are trying to look at the building blocks, and then from them, we are trying to represent the reality. Now, today we are speaking about clean energy and resource efficiency. And what I want to show you very briefly is one of the work that we are concerned with at the moment. This is chemical looping. And what we are trying to do, we are trying to produce clean energy. And this is achieved through this technology that simply takes particles oxide, metal oxides here, and they are sent, these particles are sent in a reactor where they oxidize with air. Then the oxidized particles go in another reactor, which is the combustion reactor. And in this combustion reaction, what they do, essentially the particles extract oxygen from the particles react, gives oxygen to the fuel, and therefore we have combustion, and this combustion produces CO2 and water. And of course, these two components can be very easily separated, and then CO2 can be stored. Now, how do we do that? And here we start to look at nature. Now we have to do this going through the various level, and we start from the very small level, which is the material development, where we learn how to enhance redox reactions. So these reactions are very simple in reality, and Mark Oliver has just spoken about one of the most normal, natural reactions, which is what we do when we breathe. When we breathe, we oxidize glucose and then produce CO2 and water. And then, on the other hand, plants do the converse for us and reproduce the glucose. So essentially, this is the cycle that we are going to reproduce in our reactor. But of course, I mean, it's not just about chemical reaction, it's also about transport phenomena. And in transport phenomena, we are looking at patterns, as Mark Oliver said, and this is a pattern of particles in our lab, and this is the patterns that we observe in dunes. And we are looking at these interactions in reactors, going from the way particles contact with air or with fuel, and then organize themselves. And we are learning from nature how to model that. Finally, going to the reactor and process intensifications, we look again at how nature intensified the production. For instance, by looking at some reactors, this is just an example, it's called the high G reactor, which is essentially increasing the gravity in the gravitational forces so that we can enhance the mass transfer and reduce the size of the reactor. So in conclusion, we need to be inspired, and we are inspired at each level, at each scale level, and nature can teach us how to intensify. However, I think that the final message I want to leave you with is that modeling, in my view, is an involuntary way of do nature-inspired activity, because, like I said, we are trying to bring together the building blocks and try to reproduce what nature does. So I will stop here, and thank you very much for your attention.
Thank you so much, and we're glad that you managed to find the slide. It was really great to kind of take us through that journey of modeling, and really looking forward to kind of digging into that a little bit deeper as well in the panel discussion. So that's great. Thank you. Again, keep the questions coming in for all of our speakers. Our next speaker that was meant to be joining us this morning is Nagori from ExxonMobil, but I don't think that Nagori has actually been able to join us yet. She's actually calling in from New Jersey in the US, and we believe she's having some technical difficulties, so hopefully she should be able to join by the end of the session. So we are just going to skip over her spot for now and move on to Massimiliano, who is a research fellow with the Royal Academy of Engineering and a lecturer of fluid particle systems in the Department of Chemical Engineering at UCL. Going to pass on to you now. I think you've already started sharing your screen, so you're ready to go. So I'll let you take it away.
Thank you very much, Emma, for your introduction. So in these 5 minutes, I'll try to give a little bit of an overview of what we do at UCL with this waste to fuel approach, trying to basically solve 2 of our major, if not the major problems that we have nowadays, which is waste generation. We do produce a huge amount of waste, which is very unsustainably disposed, in the best case scenario incinerated, otherwise it's just landfilled with immediate consequences towards our environment for contaminants leakage and greenhouse gas emissions. And the second bigger problem, which is still our reliance on fossil fuels, which we absolutely need to find an alternatives. And so this is the kind of rationale behind this waste to fuel approach, is trying to solve the 2 problems at all once. And let's see if nature can help us with something. So what lesson can we draw from nature from sustainable waste management? Well, this is a kind of tricky situation in such a way that nature, there is no, this term like waste is 100% man-made term. There's no waste in nature in such a way that all living matters at some point die, and they become food for a community of microorganisms and bacteria, which degrade these components and give back nutrients to the soil and emit some carbon back into the atmosphere, not as much as carbon was originally taken from the plants themselves. Now, when they are in an anaerobic environment, this carbon comes as a methane, and that's what pretty much happens in landfills. And methane is a very powerful greenhouse gases, and obviously this is some things we need to avoid. So how we can get inspiration from this? Well, the most immediate things we can do, and that we have actually done successfully, is let's try to imitate this process in such a way that basically we use the same microorganisms to digest our organic waste that we produce to produce methane, which is a fantastic energy vector for heat or transportation. And that's what anaerobic digestion has done until nowadays. And I must say that's a quite fantastic example of biomimicry nature in action, especially for those, for example, rural and applications where locally available waste can be directly converted into gas and to nutrients that can be sent back to the soil. And we collaborate at the chemical engineering department with the civil engineering department to develop such techniques also for sustainable countries where anaerobic digestion took place to be quite useful. Now, is this the solutions to the problem? Unfortunately, not. So biological processes are very useful, but cannot cope with the enormous amount of gas that we need, of fuels that we need. And currently, so we need a technique, so that's something that can exploit a much wider range of feedstock, including municipal solid waste, to be able to produce a synthetic gas which is chemically identical to natural gas in this case. And so that's where chemical engineers come to be quite helpful. There is this so-called thermochemical pathway by which solid feedstock can be thermally degraded into carbon monoxide and hydrogen, which are the building blocks for hydrocarbons, and then further reassembled into fuels. And so basically it's to stop our reliance on the fossil ones. Now, I won't have time to talk in details about how gasification works. That's a quite fantastic but also complex problems that takes in place into fluidized bed reactors, something that Marc Olivier and Raphael have already kind of illustrated, like they kind of work. So this process sits in between combustion and pyrolysis to produce what is called synthetic gas, to produce fuels. But this gas unfortunately comes with problems related to ashes. Waste is a very ash-rich feedstock, and tars, which makes that gas very difficult to be used. And so industries have tried to use the so-called plasma. Plasma is the fourth state of matter, or material that's after the solid, the liquid, and gas, that can basically take advantage of the highly ionized and electrically active environment to break down and cracks all these contaminants and ashes and basically produce a clean gas. Now this is a problem because plasma is has a very high energy cost consumptions and short life of electrodes. So again, nature comes into rescue us because we have plasma in nature. So this is as perfect examples of lightning generating in erupting volcanoes, where just basically triboelectricity from ash particles that rubs amongst themselves that produce these sparks and reproduce that kind of a highly reactive environment. And in chemical engineering, we tried to understand that underlying mechanism for spark generation and engineering a new process that can potentially generate highly active environments like plasma with a very low cost and with no need for electrodes. So these are kind of two examples that can be used for waste to fuel approach, and looking forward for the panel debates to explore these further. Thank you.
Amazing, thank you so much. And thanks for kind of giving us a really great overview of that. I think kind of one of the things that stood out was kind of that notion of kind of waste doesn't exist in nature and it's man-made. And I suppose kind of coming from a circular economy background, we always look at kind of waste as a result of poor design. So it's great to kind of, why we live in a world where that does exist, how can we learn from nature to think about ways in which we can optimize that or make opportunities from it. So that was really, really great to kind of go through that. So thank you so, so much. I am going to pass on to our final speaker of today, which is Greg, who's an academic track fellow at Newcastle University with expertise in gas separation using sorbents and membranes, as well as full chain carbon capture and storage. So really excited to hear what you're going to go through today as well in your introduction. So you're up next, Greg, if you're ready.
Okay, thank you very much, first of all, for the invitation to speak with you all today. So I'm going to talk about my work with a class of membrane called the supported molten salt membrane and their application to the separation of carbon dioxide. So the membranes themselves are made of a solid ceramic material with a liquid molten salt contained within the pore space. I'll talk about their ability to self-form, published in Energy and Environmental Science, their ability to self-heal, published in the Journal of Membrane Science, and more generally, their facilitated transport mechanism, covered in a recent review article in the Journal of Materials Chemistry A. So first, facilitated transport. You can see in the top left box, schematics of the cell membrane found in all the cells inside our body. In purple, you have the integral membrane proteins. So these can be channel proteins, such as the aquaporin on the right, which has a nice straight through shape, or a pore with a tortuosity approaching 1. Or they can be carrier proteins, like the example second to the right, where a carrier picks up the substance to be transported and shuttles it across to the other side of the membrane. And these types of structures in nature allow the really rapid and highly selective transport of molecules and ions in and out of the cell. So in the supported molten salt membranes that I work with, you also find carriers, shown in the box on the bottom left. These may be carbonate or oxide anions, they might be electrons in the ceramic support or in the molten salt. The details are not important right now, but the concept is that a carrier that's mobile within the membrane that can pick up, for example, carbon dioxide and shuttle it across the membrane. In combination with parallel pores, like you find in aquaporins, this is the box in the middle at the bottom. Here I've used laser drilling to achieve an ideal or close to ideal pore shape, a straight through parallel pore, again with a tortuosity of 1. So the performance of these membranes when you combine the carriers and the ideal pore shape is unparalleled. So this plot in the bottom right here in the blue box, the 2 orange points are these membranes, far beyond the permeability and selectivity of state-of-the-art gas separation membranes. And I'll give you a little bit more detail about that later. So now for self-healing and self-forming. The images in the top half of the green box are carbon microfibers in A, or carbon spheres in C, embedded in the ceramic material of these membranes. So if I had oxygen at high temperature and remove the carbon through oxidation, you then get the membranes that are in images B and D. So this gives me a false crack through the membrane, simulating a leaking membrane in operation. If my molten salt phase is highly wetting on the ceramic, shown in the contact angle images in the bottom of the green box, the molten salt can spread to fill these voids and keep the membrane functional. So we demonstrated this fully autonomous and intrinsic self-healing very recently. And these are the 2 key points. Healing in the body, for example, requires no additional materials and no human input for it to occur. And that's what we've done here. In the red box, you can see X-ray CT measurements. So just think of a CT scanner in a hospital, but for materials, of a self-forming membrane. Here the phase in orange, which is a highly electronically conductive metal, self-assembles into dendritic or branch-like structures with time. From top to bottom, this is with time. Once those structures are touching both sides of the membranes, you have an electronically conductive membrane using a fraction of the metal normally required. We better the performance, but we also lower the materials required, and that gives you materials and cost savings. So overall, to sort of wrap up and conclude this very short talk, I mentioned facilitated transport, and how this can redefine the state of the art for, in my case, CO2 separation membranes. They have the membranes that I've talked about today. They've got 2 orders of magnitude higher permeability than what is required for economically competitive carbon dioxide capture with existing technologies. They have CO2 selectivity over nitrogen of somewhere between 100 and 1,000, which is far beyond what is required also. Self-forming membranes, I can use 1 order of magnitude, I said metal, in this case it was silver, 1 order of magnitude less silver than membranes that are composed entirely of silver, but also gain higher performance due to this dendritic branching structure. And then self-healing membranes, the wetting and spreading of fluids into cracks, in this case, cracks that were falsely introduced, can help self-heal a membrane and in principle other devices. So that just leaves me to thank my collaborators at Newcastle and UCL, and also the funders of this work at the bottom right there. Thank you.
Brilliant, Greg. Thank you so much for taking us through that. I know there's a lot to cover there. I mean, I know within carbon capture and storage, it's definitely a priority area, certainly that's being kind of signposted by the UK government. So it's definitely, and for me, it's an area I'm definitely trying to learn lots more about. So it's been really great to kind of go through that, and hopefully we can dig into the details of that a little bit more as well in the panel discussion. So thank you so much. And that concludes all of the presentations and introductions from all of our panelists this morning. So thank you all for going through that and giving us a really kind of quick high-level overview. It's been really brilliant. I can see that we've got lots of questions coming through from our audience, which is great. So please do keep them coming. Hopefully we can answer as many as possible. And please do keep voting on those questions as well. And that will help us kind of sort out which ones you're most interested in hearing the answers for. And before I go over to George to kind of start posing some of those questions to the panel, I mean, each of you have given really quite a broad range of examples around kind of where we could start to explore the opportunities for nature within clean energy and resource efficiency. And one of the things I kind of wanted to kind of put to you was around kind of where do you see the potential to use some of these principles that you're applying within your own work, and how that could be maybe used in other applications as well. So I don't know if anyone from the panel kind of maybe wants to take that question on first.
Well, I'm happy to.
Perfect. Thank you.
So there's a whole lot of possible applications. I mean, here we focused on energy and resource efficiency, and you see already the breadth from all the very nice presentations you've heard. I mean, the point of having a methodology, as I was explaining, and as I came up in some of the other talks, is that in this way it allows to do some lateral thinking, right? So if you do more than narrow biomimicry, and you look at imitating nature, but you look at mechanisms, then you have an ability through these fundamentals and through design approach, right, which we've seen from fluidized beds to fuel cells to membranes in these presentations, then you have an ability to use that validated approach also for other applications, right? So what we've seen, for example, in a PM fuel cell can then be used also maybe in battery technology. What you see in one type of membrane may be used in another. But not only that, you can see how you can hierarchically structure porous materials, say for catalysis, but then also use it then as an adsorbent, and see how transport phenomena inspired from structures that you see, for example, in leaves and you see in lung tissues, and what we can learn about the dimensions of those and the principles behind the transport, which go from flow to diffusion. What can you learn from this to design new type of catalyst, porous catalysts that could be better for environmental processes, for cleaning up or for converting chemicals into more desired products selectively, or you can use it as we've done, say, in dental materials, so that you have much faster osseointegration, so it grows more faster in the bone, or for new building materials. And so that's the exciting thing, that you then can apply something in one area and apply it to another one. And so that's the acceleration in innovation and application.
Yeah, absolutely. And I think, I suppose, kind of with the Centre for Nature Inspired Engineering, that allows you to kind of work across a number of different application and sector areas and kind of do that cross-sector collaboration to encourage further research and innovation as well. I didn't know if any of the other panelists wanted to pop in on that one. Yeah, Raffaella, I can see you've got your hands up.
Actually, I would like to comment on that by also answering to two questions that are one to the panelists and one to me specifically. And I would like to link what I'm saying now to those two questions. Of course, I mean, when I look at the model, there are methodologies that we can learn from nature that we have to extrapolate to many other phenomena. And in fact, there is a question about, the question says, keeping molecular level granularity is clearly not practical when dealing with macro scale. And that's absolutely true. And this is how we can extend. Now, I want to give an example to explain how we can do this looking at nature. If you look at the kinetic theory of gases, okay, you don't need to understand how each single molecules behave to have a measure of the pressure in a gas, okay? This is exactly what we are trying to do by looking at not at the molecular level, but doing this averaging and homogenization techniques that nature does in a way to look at a large collections of granules, and therefore for particles specifically in a reactor, we are not going to look at the single reaction, at the single particles, how each single particle reacts, but we are going to look at the global behavior, just learning from nature how to do the average, the right average. And the next thing, it was also another question that was answered. How can you extend this to human interaction? And it's a very good question, because actually in the past, we have tried to model with the same theories for granular materials. We have tried to model human interactions, for instance, when imagine that, well, a very bad example, something happened in a stadium, there is a problem and people have to evacuate. So you want to understand how people interact for the evacuation, and you can learn from the granular materials. However, what is difficult is that here comes the human nature, and the interaction between particles is well known. The interaction between humans is much more difficult. However, as people have actually said, we have, for instance, nowadays, we have, for instance, the autonomous agents. And that can be something that can help you in understanding that interaction. So I think, yes, we can extrapolate and translate what we do in one field to the other one, and nature does that in practice.
Yeah, absolutely. I think there's just so many layers to consider, isn't there? But I think there's always a way of being able to take inspiration from that. And kind of, I think, over the last couple of weeks, I've been working with a colleague who's been doing mathematical modeling, and it's really kind of opened my eyes to the opportunities and potential that there is there. And I think, it's really exciting to actually be able to see that, things that I didn't think that would be able to be modeled. And I think it's really important as we kind of, I suppose what we hope with these webinars anyway is to hope kind of spark that inspiration around kind of things that you wouldn't have thought could be done or aren't being done, might actually be able to apply it in the sector, the application area that you're in, to try and help kind of promote a different maybe way of thinking or a different approach to these things. So that's great. I'm quite conscious we've got loads of questions in the Q&A box and we haven't addressed any of them yet. So George, are you there? And do you have a couple of questions you'd like to put to the panel, please?
Hi, sure thing. And by popular demand, based on the votes received, we will start with Mark. So, Mark, how do you create the connection across the vastly different scales? So, for example, from a leaf level to an ecosystem in your research?
Yeah, that's an excellent question. We only had so much time to go over it in the presentation. But there goes a lot of work behind that, isn't it? And what I found exciting over those years when I started, say, developing the fractal injector, that was 20 years ago, believe it or not. And at that moment, bridging those scales, it seemed nice. And you could build this, you can construct it using different pipes that you would put together, assembled together. And maybe you can weld them together and create a larger, say, fractal injector like this, a tree-inspired or lung-inspired ones. Nowadays, with the advances in additive manufacturing, 3D printing, selective laser sintering, and so forth, it is amazing what one can accomplish. Just very simply. I mean, if it is, say, using polymeric materials, it can be done often in minutes. You can create one of these injectors, these flow plates from the fuel cells that I showed, of scaling these and bridging these different scales. It was done by selective laser sintering, which is still quite expensive with metals. So now we turn to using printed circuit boards, which we assemble together. And so for these fuel cells, which we can then lower the cost by more than an order of magnitude, okay? In fact, we go from about $1,000 to maybe $10, $20, okay? So, and then at the structure of the catalyst, the question goes from the nano to macro. There's also been enormous progress in material synthesis, in the synthesis of these, like these hierarchical catalysts I was just talking about earlier, and these dental materials we're making, and which we are commercializing at this moment. So there you, again, have tremendous progress. And the same can be said in the whole field of nanoscience, right? So the whole, what we do is with nature-inspired solution, nature-inspired engineering, we're talking here about the methodology, and where also modeling plays a key role, as Rafaela has discussed. But to actually realize this in the end, we have this tremendous progress in manufacturing methods, which are not just top-down, but also bottom-up, but also top-down, different types of micro machining methods, different types of 3D printing methods, and so forth. And that's what makes it possible to link scales and to create things that before were impossible. Yeah. So.
Perfect. Thank you so much for that. And the second question for you, again, it was pretty much equal on votes, is if you've seen any performance benefit for your fractal structure for fuel cells or in fuel cell applications.
Definitely. So again, we are driven by trying. I'm an engineer, and I work with a broad team of people. We try to actually solve problems, right? And for the fuel cells, we've been collaborating with the Electrochemical Innovation Lab at UCL, the team of Dan Brett and colleagues. And so there, what we really wanted to do is having a much more stable fuel cell, a much more scalable one as well, one where the catalyst is better utilized. And so we can increase the catalyst utilization. So you need much less catalyst to produce the same power density or current density. What we see with our fractal flow plates when we use these is that this is much more scalable, say from a small one to a larger one that you build just by changing the number of branching generations, but keeping the size of these last outlets constant and the distance between them. So it's just like an ideal shower head, if you want, right? So you have this very uniform gas that's being distributed, and then the collection of the products. And so you have much more stability in this way. And the current density and the power, which is the current multiplied by the voltage, is also increased. Plus, through this capillary system, right, inspired by our thorny lizard friend, we are able to manage the water as well much more easily. So if water is produced, rather than condensing and blocking, we have this water management scheme by which we can evacuate water more easily. So it's in a whole range of performance benefits thanks to this nature-inspired approach.
Perfect. Thank you so much. We're moving to Rafaela. Keeping molecular level granularity is clearly not practical when dealing with macro scales. Can you comment on how you decrease the level of granularity while still sustaining the accuracy of models as you go to higher scales?
Yeah, sure. I think it was something that I tried to say in my previous comment. Anyway, what we are trying to do in practical terms, we are looking at a way to do average and homogenization techniques. And like I said, again, we are inspired by nature, because in nature, you don't see the granularity of atoms, for instance, when you look at the flower that I have just shown you in my picture. So essentially, we are going to do mathematically writing down homogenization and averaging techniques. And like I said, it's like doing the kinetic theory for gases, where you start from the single molecules of gases, and through the average, you get the measure of the pressure, of the diffusivity of the gases. And it is a very precise measurement, very precise prediction that you can do. And so we apply exactly the same kind of methodology in modeling to lose the granularity and look at the macroscopic results of our model.
Perfect. Thank you so much. We're moving to Greg, as I know that he has to leave early, and he already had a head start as he's already started answering in text to most of the questions, but I kept on for him. So has the self-healing membrane been tested and demonstrated reliability in different engineering applications?
Yeah, so thank you. And yes, I have been trying to quickly fire through some of these questions, so have a look at the Q&A answered section. So far, this has been tested in carbon dioxide separation only at high temperature. In the future, I would like to look at this more generally. It's gas separations that I work with. The key point here was that it's autonomous and that it's intrinsic. You haven't added a self-healing material to do the healing, and you haven't added anything or done anything to trigger the healing to happen. So in the approach that I've developed, it's about the wetting of a liquid on a solid, and that liquid is both the selective phase for the separation, but also if it can heal any cracks or voids formed, you can see how that both heals the membrane but keeps the separation device working. So I'd be interested to look at this for both different gases, as in the separation problem, but also different liquids.
Perfect. Thank you very much, and thank you for answering the questions in text to those people. I'm moving it now to Emma, who has some news.
Yes, hi, and thanks, George. Nagori has been able to join us. Thank you so much for being able to pop in. I'm not sure we'll have time just to kind of go through your short presentation, but I know that we kind of had discussed what would be the topic of what you'd be covering. So I was hoping I could kind of just answer you pose a question to you, and then we'll bring it back to Massimiliano, because I know we've got quite a few questions for him in the box, and then we can do the summary if that's okay, Nagori. So I know that your presentation was going to kind of focus on, I suppose, traditional industries and how they're focusing more and more on environmental impact. And I was wondering if you'd be able to comment on where do you see the potential of, I suppose, nature-inspired engineering in this development?
Right. So I think, yeah, so our company, and especially my research since the beginning, they focus on nature-inspired solutions because, so maybe I can give my little brief 5-minute introduction, if you don't mind, because I think otherwise it won't really make sense, my answer. But
yeah, we should have a couple of minutes for that before we close at 12. So yeah. So yeah, my research lies in the interface between process technology, modeling and optimization, and life cycle assessment. So in a way, we discover, I discover kind of like principles and mechanisms also that govern the processes and technologies that we develop. But also we use artificial intelligence and data analytics to actually expand the impacts of those insights and find sustainable solutions for our societies. So the most important part of my research is really related to finding competing objectives and different optimization mechanisms that actually drive the reactions and the processes that we discover. And in that respect, I work in ExxonMobil Research and Engineering in labs in Clinton, New Jersey, and I am part of the process technology development team. So our department is very well known for catalyst development during the past decades. And one example that comes to my mind that actually really draws from nature-inspired solutions is our catalyst for benzene alkylation with ethylene and propylene. So actually our MCM22 and MCM45 zeolite replaced solid phosphoric acid and aluminum chloride in a process to produce polymers. That process really mimics enzymatic natural processes, and catalysts actually help us produce cleaner products and more efficient and make more efficient use of the energy in our processes. Our technology involves a really wide portfolio from bioenergy to membranes and carbon capture and utilization. And in particular, making biofuel from algae really makes use of natural processes like sunlight and microorganisms, as well as our direct air capture processes, process research. It's aiming to find ways to optimize natural processes like that plants actually do, but using more efficient, using the resources more efficiently, like land and water. So in that way, I think I'm very passionate, and I think our processes already grow from nature, but there is a lot to explore. And I'm very passionate about finding practical applications for nature-inspired solutions. And I have to apologize because the seminar was announced for me like at 11 a.m. and I was thinking that I was joining early actually. So apologies for that. Yeah. No worries at all. I know that you're calling in from New Jersey, so it might be kind of time difference and Yeah, I mean, I think, yeah, changing the clocks in British summertime, so I'm sure there might be some confusion there, but we're really pleased that you were able to join at least before we managed to close, and at least kind of give a little bit of an overview of kind of the research you're doing and also the focus and kind of from ExxonMobil perspective. So it's always nice to kind of get an overview and input from industry as well, and kind of see how research and industry is kind of working together to move forward with this agenda. Massimiliano, I know that we've been haven't managed to ask you many questions as well, but I think we do have one here from the audience we would like to put to you. George, are you there? Have you got it?
Hi, Massimiliano. Can I ask if it's possible for you to tell us what is the technology readiness level of gasification from waste technology?
Yeah, so gasification per se, I mean, that's already industrial applied, especially for energy production. Now, if we talk about waste to fuels, so converting waste into fuels via gasification, that's a different subject. So we are around, I would say around 7%. So there are a number of demonstration, so TRL 7. So there are a number of demonstration scale plants which have starting operation, and 2 we have here in the UK, and a couple in the US and in Canada. So hopefully, we hope that by the next 5 years, we should see the first industrial waste to fuel plants on operation.
Perfect, thank you so much. I have a general question for the entire panel. So, do the panelists agree that there could be a benefit from a chimera approach, the combination of a number of nature-inspired activities or solutions in a way we would never see in nature? Not sure if you can go ahead first, Massimiliano, since you already unmuted.
Yeah, no, I mean, I start quickly on this, and I think yes. As I tried to prove on my presentation, for example, on the waste management approach, which we cannot just leave nature to fix our mess, and and having just normal biological process to deal with that. We need a systematic and multifaceted approach onto that. So I would say the future of waste management and fuels and energy, kind of combinations of different solutions and different nature-inspired solutions. So I would say yes. So definitely we need a concerted efforts from different aspects, and perhaps using the mechanisms which in nature exist to design and develop new processes that can help fixing the problem.
Perfect, thank you very much. Anyone else in the panel that wants to add to this?
Yeah, I would like to add that I absolutely agree. For instance, when you try to intensify in terms of having a higher gravitational force, for instance, you are intensifying something and you are doing nature in a different way. But I think that, for me, more than scale, probably what we can gain is time. So in other words, what I think that we have to learn from how to intensify what nature does over a long time in a very short time. And in a way, it's what Massimiliano also was saying, is when you produce how you can intensify and produce materials that have been like, for instance, biochar, which has been used after many years from nature, and you do it in a lab and you do it faster. So yes, we can intensify, I think, and do something which is much more effective. That's my opinion, yeah.
Thank you very much. I see Mark, I think, wants to add something.
Yeah, I could always add something. I think I completely agree with my colleagues, but perhaps it ties in even to another question that came in about photosynthesis. There's something where, again, when we look at nature, right, there's so much to be learned, but at the same time, photosynthesis by itself, the efficiency is extremely low. right? And so we shouldn't copy nature. That's the whole point of what I have a bit against, say, the narrow biomimicry, right? So it is learning of these principles, how it works as a system. And also, as Massimiliano emphasized, there's no waste in nature, right? So how does it work? So one step by itself may be inefficient, but there's a whole, the whole process may be very robust and resilient. And we should then use some of the principles in nature that lead, say, to very high selectivity and to high stability and to high resilience of the whole. But then maybe, as Rafaela was saying, time may be against us. And so we should see how can we accelerate some of these steps? How can we actually create this in an environment using perhaps a different context? So we shouldn't necessarily work, nature has different contexts. It must work, say, at a particular temperature, right, atmospheric pressure, but we can use different pressures, we can use different temperatures, we can use different materials as well that we can create. And in this way, we can use some of the advantages of nature, but then use our insights based on experimentation, based on theory and modeling, and then apply that to realize solutions that have these benefits, but complement it with, say, a higher activity, a higher overall shorter times, right? So that's the key, I feel, in terms of nature-inspired solutions, right? It's just to combine the best of nature, all this enormous book, right? The open book of nature with the beauty it has, but the many mechanisms we need to unravel, right? But then also know how to apply and adapt them to the context of technology and also a context, right? Which may be social context and economic context and so forth.
Thank you very much. I've been told we only have time for one last question, and it is a panel question. And this time it actually includes Emma as well. So how do we avoid repeating the usual UK problem of the research being done in the UK, but all the economic exploitation being undertaken elsewhere? And Emma, if you are to be the first one to start, and maybe about how the KTN can help with that.
Yeah, absolutely. Thanks. Thank you, George. The whole reason I'm chair is I'm have to answer questions, but thank you for putting me on the spot anyway as well. But I think within the KTN, I mean, we have a lot of tools and a lot of kind of experts that run across a number of different sectors and application areas. And I suppose through that and through the work that we do around kind of, I suppose, understanding helping to kind of understand what the ideas are that are coming through, understand the UK's capabilities to help take these ideas to market, and understand as well where would the biggest impact be of those ideas and what application areas they could lead to. And I think the way that we are set up within the KTN is really is a really perfect way to be able to help kind of bring kind of those ideas right through to the application area, and understanding as well kind of, I think, you know, we are very much kind of, I suppose, set up to kind of create positive change, and we've got deep expertise in a number of different sector areas as well. So it helps us be able to develop those insights into kind of what the capabilities might be for the UK, what those strengths are in various different kind of sector or thematic areas, but also those regional strengths and how we can build in those and connect, I suppose, the position that we're in to be able to connect research institutions and researchers like the panelists we have today alongside industry and public and the public sector as well, to kind of create this really great environment where we can take research and innovation and ideas right through to kind of commercialization and deployment. And we see there's a really great opportunity for us to be able to do that through the special interest groups that we have, like this one, also looking at kind of the landscape maps that we're developing in a number of different sector areas, including, you know, my colleagues and my team working within quantum and looking at kind of the role that the UK have within that sector, and kind of what are the strengths for us to kind of bring that through and exploit the economic benefits of that. So I think there's lots definitely going on with within the KTN, and I think it's really around that kind of being that ability to kind of connect with so many different audiences and bring that together and raise visibility and awareness and develop those insights and kind of then report those back to the people that need to know about it, so we can then harness further investment in the right areas and at the right TRL levels, as well as to kind of expedite and kind of accelerate innovation happening and being exploited here as well.
Oh, thank you very much. That actually sounded perfect for an improvised question, like impromptu question. So if anyone in the panel has anything to add to what Emma said, and maybe from your own perspective of what the UK can do.
No, perhaps I can add something. I mean, Emma phrased it very well, but perhaps related to the nature-inspired solutions by itself, I think it is approaches like this. If we can do something that is truly transformative and different, and it stimulates people from very different backgrounds to work together and give them an encouraging environment, right, to take their ideas further and excites them, many of them will find it, at least in my experience, will enjoy actually a path to a career they haven't envisioned before, which is one that is more entrepreneurial. I mean, some do want to be an entrepreneur for many years, but others I've seen grow to be one, and they get excited, especially by working with people from very diverse backgrounds. And also that some of their technology may be more than end up in a journal paper, but perhaps be the start for licensing, patents and licensing, and then and in this way, including, I hope, through events like this, we may actually stimulate others to join us. There is a whole ecosystem there as well of people who are investors, other companies that may be interested to collaborate. The CNIE, we collaborate with several companies, and people taking their ideas forward by forming new connections with others, with complementing experience. Yes, it may be a challenge sometimes, depending on the context, to do something here and to find the right investment. But that is something where, when I think, even especially in times like this, okay, when we are living through a serious crisis, it is exactly the type of innovation and transformative thought and the differences that will make us stronger, where we can really make a difference. And so this is the moment to invest, in fact, and start new areas of work, new businesses. So, you know, this is something we can do.
Yeah, that's a really hopeful and optimistic note to end on. So thank you very much for that. I think, yeah, it definitely fills me with a lot of optimism if we're able to kind of come together and react to the current crisis that we're all faced with across the world, and kind of react really quickly and, yeah, have that transformative change. Then it kind of fills me with the hope that we're going to be able to kind of work together, hopefully, to kind of respond to climate change and to overcome that, and also to reach our goals around net zero and some of those kind of sector goals. So thank you so much for that. And I think it also leads in really nicely to kind of my summary slides. Thank you so much, George, for all of those questions from the audience. That was brilliant. I think you selected some of the some really great ones. So that's fab. Just to finish, I know we're kind of slightly over, but it kind of just links into kind of the nature inspired solutions. Like the kind of the aim of this, and I suppose what we've been looking at, is kind of the special interest group focuses on 3 application areas, which is around transport, energy, and infrastructure. And the idea is to really bring together a diverse community and raise the profile of nature inspired solutions within these application areas, and to develop ideas for collaborative projects and to identify unmet needs within a target industry. These industries might not be saying we want a nature-inspired solution, but what we want to be able to do is kind of inspire a different methodology and a different approach, and to kind of look at ways in which we can, again, harness the ideas within the UK and kind of find a way to plug those into kind of active application areas and sectors and exploit the results of that here. And also, as well as that, how can we kind of share that and showcase that to the rest of the world as well, which is really important. This is the 3rd session in our Nature Inspired Solutions webinar, and it will be coming to a close on August 28th. This will be the final one that we have got planned, which focuses on future flight. So if you are interested in kind of the role nature might have in that space, then please do join us. We have 2 speakers already lined up, one from a university, Sheffield spin-out called Optera, and then also Airbus as well. So it's promising to be a really great lineup. Been really great conversation today, really great dialogue, really great engagement from the participants and all of the panelists. And if you are keen to keep the conversation going, please do so. I know there's never seems to be enough time in these panel discussions, even though we left even more time today to cover all of the questions, to go into all the details of the things we want to discuss. So if you do want to continue chatting about this topic, then please do go over to Meeting Mojo and go grab your lunch between now and 1 o'clock and get on there and book some one-to-one meetings in and continue chatting. We'd be really happy to see you on there. But that kind of concludes our 3rd webinar session on nature-inspired solutions in clean energy and resource efficiency. I'd like to thank my colleagues Poonam and George so much for all of the background work and being hands-on today and being able to help pull all of this together. Oh, I think I said the wrong time, from 1 to 5 p.m. Thanks to George for that. But also, as well as that, thank you to all of our amazing panelists and speakers today as well. It's been absolutely brilliant for you to kind of come along. And I know 5 minutes never isn't enough, and we could have each of you speak for an hour on your topic areas. But thank you so much for being able to join us and just give us an overview and a glimpse of kind of some of the amazing work that is happening within kind of UCL and Heriot Watt and Newcastle, and also ExxonMobil as well. It's really inspiring to see. So thank you all so much, and we hope to see you again at the next session on the 28th of August. Take care.